if you guys do me a favor, grab your chapter 3 Lumineer. This book is down to earth. I don't know if I told you guys 6 years ago we used to do the IES manuals books and they were that thick. It gets into the construction of the eye, the rods and the cones and how the eye sees and all this good stuff, and it was really way more details than we needed to be. This is just down to earth, how we do lighting calculation by hand, what's the science of lighting, and what's the fixtures and what's the lamp. If you guys remember yesterday, we talked about lamps. The first thing we talked about the nature of light, and then we talked about lamps yesterday, different type of lamps. Today, chapter 3 talks about fixtures. Fixtures or luminaires. Morning, Ashley. I thought your car didn't start today. Okay, so if you guys go to chapter 3, I will really appreciate it. So a couple of things about fixtures. This chapter has a lot of good stuff to read, but here's what I want to highlight. I want to highlight a few things, as you guys can see. It talks about luminaires. Luminaires is the technical terms that we use for a lighting fixture. Even the NEC code book lately adopted the term luminaire. They used to call it lighting fixtures. They adopted the term luminaire. Luminaire or a fixture, lighting fixture is right above your head. If you guys look at that 2x4 troffer right above your head, this is exactly what we're talking about. When you have a luminaire, first of all, you have the housing. We all know if you open that one, you guys have opened it with us. Did you wire any of the luminaires in the lab? When you open any luminaire, you're going to have that frame, metallic frame, aluminum or steel or whatever frame to hold the fixture together. That's what they call it, the housing. Why do we have a housing? Because we have troublemakers like Chad who likes to bust things when they're working, so they don't bust the lamps and the ballast. So they put them in an enclosure that they call it housing to protect the electrical connections, the ballast, as well as the lamps, right? So that's the housing. Everybody knows what a housing is, right? Take this, if you look at it, that little box that you put the fixtures and the ballast in, it's called the housing. The second thing that we have, guys, inside, if you open this one, most of fixtures will have something called reflector. Reflector, if you open this lenses here, you're going to see that right above the lamps, you're going to have a very a reflector, which is very what's the word when you reflect things? Very smooth reflecting surface. And the idea of the reflector, guys, because we're doing lights, every time you have a smooth surface that can reflect light, you get more foot candle. So the smarter than Chad, instead of the housing itself reflect the light, they add inside the housing a reflector. We call it parabolic reflector that reflects. Some of them are parabolic where they can reflect in a parabolic terms, shape. So the reflector's job is to direct the light, nothing but directing the light. So instead of the light going all over, Rob, we shoot the light directly where the light should be. Questions about reflectors? When you guys open it, you're going to find the housing. Inside the housing, you're going to have a reflector. When you move out of the reflector, you're going to have something called diffusers or louvers. What you're looking at right here is called diffuser. The louvers, you remember that little squares, guys? You've seen the little squares. We used one of them in the offices. They're squares. It looks like this with a lot of squares and pigeonholes. Looks like a pigeonholes. So these are your louvers. The louvers and diffusers have one main function. Well, two main functions, Ashley. Main function number one is to distribute the light evenly, so I can see Nick's head and Chris's head the same brightness. That makes sense. They distribute the light evenly. And the second one is help sensitive hearted people like your friend Chad to feel comfortable under the light because they hide the lamps. I don't know how many of you guys walk around and look at the lamps. If you take the diffuser down and you look at the lamp, it's very uncomfortable for us as a human being, especially the sensitive people like your friend Chad, to look at the lamp. Your eyes get irritated by the lamp. So the diffuser is supposed to do two things. Number one, distribute the light. And number two, hide the lamp so it makes you feel comfortable when you look at the light. Not like when you're looking at the light all the time. Any questions about the diffusers and the louvers? Different diffusers, different louvers, but their job is to distribute the light evenly as well as make you feel comfortable under the lamp. The fourth thing in any lamp that you're going to buy almost is a lamp, right? We have the housing, we have the the reflectors, we have the diffusers or the louvers. The second thing, up to this point, we're talking about mechanical equipment. up to step number 3, guys, this is just mechanical equipment. There is no difference up to 3 between what I described and that cabinet sitting on the wall here. It's just a mechanical things, right? Now we move into the electrical. We have to throw a lamp inside that fixture or that luminaire. Make sense? A lamp. Now lamps, yesterday we talked about lamps, guys. God forbid you put an incandescent lamp. No. Well, we could, but not no. Fluorescent lamps, most commonly you're going to use probably. LED, yep, this is the new technology that's going to be coming. High intensity discharge, that's another option, or induction light. All these sources of light, guys, are the lamps that you can install in this fixture. Any comments, any questions?
Is a few lens part of the considered part of the diffuser louver process?
The lenses or the louvers, yes. Lenses, louvers, diffusers are part of the diffuser, diffuser or louver process. Absolutely, lenses to distribute the light. Any question, guys, about the lamps? We talked about the different lamps. Most likely, 90% of the time, you are going to be at the fluorescent here or metal halide if you're outside, or LEDs now because we're becoming environmentally friendly. Lamps. And we talked about lamps yesterday, how they work and all this good stuff. From the incandescent lamps that, God forbid, that can cook 2 eggs for you on them, very inefficient, all the way to the most efficient ones, LEDs and fluorescent and high intensity discharge. Okay. So now we change a mechanical piece of equipment into an electrical by adding a lamp into it. Up to this point, guys, we haven't connected the power to it yet. Then a lot of lights, commercial lights, will have something called the ballast. We talked about the ballast yesterday. There are 2 reasons for the ballast most of the time. Number 1 is pump the voltage high enough, because most of them are arc. Most of these lights are arc. You need to pump the voltage from 277 into thousands of volts high enough, so you can start the arc. When you pump the voltage high, you start an arc. Now you started the arc. The problem with the arc is it sucks a lot of current. Then that baby on the wall here, the circuit breaker, will think you have a short circuit or a ground fault. It's going to trip. So when it started, now we started the arc, and at the same time, when the current starts going through the arc, it chokes the current, reduce the current down, so to an acceptable level, so the circuit breaker doesn't trip. Make sense? For the most part. They have electronic ballast that can make them run efficiently, guys. The lighting fixtures, the lamps run more efficient and so forth. But for the most part, pump the voltage to start the arc, choke the current to maintain the arc so the fixture can give you light. Any question about the ballast? If you have high intensity discharge or have fluorescent lights, you're going to have a ballast. If you have an LED, you have, instead of the ballast, they have a driver. They call it a driver, which is take the driver, take an AC 120, digest it, convert it to DC, and dump it across these little diodes so they can ignite. So that's your ballast, or driver for LED is called. In the past, guys, the ballast used to be electromagnetic. It's like a transformer. You cannot specify a ballast that's not electronic anymore and meet the energy code. You almost always have to have an electronic ballast with lights, as well as high intensity discharge to a certain limit. So for almost always for indoor, at least for indoor, you will be talking about electronic ballast. You bring the voltage here, and the electronic ballast will bump the voltage. The way we work, and I don't want to go even there, they control, the electronic ballast guys control the magnitude and the frequency of the wave. They make the lamps run at different frequency than the 60 hertz. So there's a lot of control going on. Who cares? They make them more efficient, Chris. The idea is to make them more efficient.
Do you have an idea what kind of voltages are on a traditional fluorescent like we have here? What type of voltage you're raising to?
I would say the electronic ballast, I would say thousands of volts if I have to guess. I really don't know exactly what the voltage that they're running at. And the electronic ones, they run at different frequencies. I think there's something like thousands of hertz that they can run these to make them more efficient. But there's more information, guys. I'm not an expert in ballast. There's a lot of good information in the back of this book about ballasts, electronic ballasts and the frequencies and the hertz that they work on, how they work. We're interested on specifying them in our project, and they work good. And at this point. Okay, the last thing, up to this point, you're worthless. Everything that you've done up to step number 5, it's not going to fire until you bring what? circuit, that's where you and I and Nick and Rob, my friend, and Phil come to place. You guys up to step number 5, this is you do it in visual. You drop the fixtures, you take it from visual into Revit so you can throw the fixtures and circuit them, bring a circuit. And we did calculation on circuit, right? Remember how we did this calculation? We said 20 amp circuit, we don't load it more than 16 amp continuous load. Based on the volt amp, divide the volt amp of the fixture by the volt amp of the circuit, will tell you how many fixtures, 16, 17 fixtures, sometimes 20, 24 fixtures you can put on a 20 amp circuit. Any question guys about this? This is your luminaire. There's no gimmick to it, nothing. Any question about this? There's a few things that I want to emphasize. There's something called CU, and Nick was talking about yesterday. The CU, it's called coefficient of utilization. Every fixture that God created has, by manufacturer, a term that's called CU. CU is a percentage. So Ashley, if you look at that fixture above you, that fixture, based on the geometry that you put this fixture in, it will make it 70% efficient, or 80% efficient, or 90% efficient, based on the location, the height, the location, the dimension of the room that you put it in. So long story short, you guys are going to be, later on, we're going to be using a coefficient of utilization. It's a function of the fixture as well as the geometry that you put the fixture in. And I'm going to stop right here because later on, we're going to be calculating that coefficient of utilization for fixtures based on the fixture itself and the geometry, reflection from the walls, the ceilings and the floors and so forth. But remember, every fixture have to have a percentage of it lost. The light will be lost. The last thing in this, guys, is called the glare. Glare is not a big deal, guys, in indoor lighting. In outdoor lighting and street lights on highways and interstates, it's a big deal. When I don't know if you, yesterday I heard you talking to Joe about street lighting, and I don't think they do it, do they? They don't do street lights. Street lights, when we do street lights and highway lights, the single most important things that they do, guys, is glare. They don't want you to drive down 494 or 94 at 75, or if you are neck at 95 miles an hour, and right in the front of you will be blinded by that very bright light. And I'm not going to tell you what's going to happen next, accidents. So glare is a big deal in highways, especially in highways, as well as outdoor lights. In indoor lights, it's a big deal, but not as of a big deal as in outdoor lights. So glare, you can minimize the glare by hiding the lamps. Step number 1, to make you feel comfortable under any lamps, the Smarter Than Chad discovered, look at that lamps here. Hide the lamp. If you look at this lamps, it's more comfortable to look at the lamps if they're hidden by lenses, of course, or louvers, than if they were not hidden, if you're looking directly at the lamps. So if you tell that to Mr. Ryman, he might disagree with you because he likes to take his lenses and look at the lamps. But you have to hide the lamps to feel comfortable under the lamp. Okay, any question guys about this? The luminaire, what a luminaire is? So this is what this chapter is dancing around when you read it. Really, this is the concept that it dances around. Any comments, any questions? Oladipo, my friend, makes sense? Very common sense. You're nothing, no rocket science. Now we know what a fixture is. We're going to go install this fixture. Now we know what the fixture is, what the component of a fixture or luminaire. We're going to go install this component of a fixture or luminaire in a building. When you install them, there's a few things you have to keep by code aware of. Number 1, is the fixture going to be inside, most likely dry location, or is it going to be outside, wet location? That's kind of divider number 1. Am I installing this fixture in a wet location or dry location or damp location? Most of the time, dry, damp, or wet location. If it's wet location, I'm not going to tell you the fixture have to be rated for wet location, meaning the lamps have to be completely enclosed, so the snow in Minnesota, the rain, the wind, whatever, we were talking about the bugs accumulation yesterday, bug accumulation, all this good stuff, if it's outdoor, has to be completely enclosed so we minimize the interference of the elements with the fixture. That makes sense? If it's outdoor or in wet location. Doesn't have to be, by the way, outdoor to be a wet location. Could be in car washing places and wet location. So first of all, when you install a fixture, make sure if it's outdoor, it has to be rated for wet location. Indoor, it has to be most likely dry location. Wet or dry location. So that's the main divider. Any question, guys, about the location? Step number 1, wet or dry. Makes sense, right? The second one is hazardous location. We'll talk about hazardous location, guys, in in the industrial project, class 1, class 2, and class 3 hazardous location. Am I installing this fixture in a flammable gases location, gas stations? Class 1, flammable gases. Div 1, the hazard exists at all times. Div 2, the hazard exists if there is abnormal condition in the plant, for the most part. So am I installing it in a class 1 location, flammable gases? Am I installing it in a class 2 location, combustible dust, magnesium dust, any of these dust that could be combustible dust, explodes and ignite, combustible dust, class 2 location, or ignitable fibers? Am I putting it in a fiber place where there's a lot of fibers, grains and so forth, where you can, where it has to be tight connection and so forth? So these are the 3 locations: div, class 1, class 2, class 3. These are 3 classes. It goes from the flammable gases to combustible dust to ignitable fibers. And also div 1 and div 2. Div 1 is the hazard exists at all times. That's the worst of the worst. Div 2, the hazard exists under abnormal condition because of malfunction or an area adjacent to a class 1 location. Any question guys about the classification? So if you are in an area that's classified, this room is not classified. They call it non-classified rooms. So I can install a dry location fixture like one above your head, move on. Had this been a gas station, and Oladipo, my friend, is a pump and dispensing pump gas station. Now right around the gas station is going to be a class 1 div 1 and class 1 div 2 location. If you are to put a fixture in that particular area, in certain location, you might have to have an explosion-proof rated fixtures. Now that will get you 10 times more expensive than the right one. The one. I'm going to leave the explosion-proof fixture, guys, and dust-tight fixtures and all this stuff until we move into the industrial project. That's where we hit the industrial stuff. Any question about the classified location? If you don't have a classified location, which in this project, thanks God, we don't. Next project, we will have a class 1 div 1 location where you guys are going to go to visual, grab a fixture, explosion-proof fixture, into visual, dump it into a room and do calculation on a class 1 div 1 location, then take it back to Revit and circuit that baby. Okay. Any question guys about the classification of the location? First of all, non-classified location, dry and wet, and then you have the classified location, class 1, 2, and 3. The gases, the dust, and the fibers. Another thing that you have to keep into consideration, guys, when we deal with is the voltage. Nick, Chris, you remember when we were picking fixture, we always saw multi-voltage, and we were picking fixtures. You can burn fixtures in the US at 120, at 240, at 208, at 480, at 600 volt. I can burn a fixture at 600 volt, guys, in certain application. As a matter of fact, you can burn it at a higher voltage than that. Burn it. When I say burn it, bringing it to the ballast. Bringing the voltage to the ballast. A lot of application in our project, guys, we're bringing the voltage to the ballast at 120. You actually can have a ballast that can run at 208, more efficient. What's the advantage of higher voltage? Anybody can tell me? Higher voltage, more efficient equipment. If I have a parking lot light, would I pick a 277 for that light or 480 if I have my choice? I would pick 480. I'll take 2 phases to the ballast and burn that ballast or power that ballast with 480. Why? I can put more fixtures on 480, number one, and I can push the current longer distances in a 480 voltage than in 120. Much longer and more fixtures.
Multi-phasing help?
Multi-phasing, usually most of them run in 2 phases. I haven't seen I'm sure they make it. I haven't seen a fixture that run 3 phase. I guess you can make a fixture that run 3 phase, but all what you have to do is just connect them in 3 phase configuration. But a lot of them they run, everybody knows what they do when they have 2 phases, guys. When you have a 2-phase fixture, so here's phase A, here's phase B, here's phase C, phase A, phase B, phase C. And when you put your fixture, you just put them between 2 phases. Here's one and here. I have another fixture. This is between this and this. And then I need another fixture, that fixture between this. Did I capture all of them, right? So one between A and B, and one between A and C, and one between B and C. Here's a 3. It looks like a 3-phase, right? It's fit from 3. There's no neutral. There is no neutral. Any question, guys, about this? So that's the voltage. A lot of ballast right now, guys, to make it easier for people, they say multi-voltage. Bring it on. You can bring either if it's electronic or magnetic, you can bring any voltage. You can rewire the ballast, or you can bring the voltage, and the electronic ballast will recognize whatever voltage you bring from 120 all the way to 600 volts or 480 volt, and it will actually, you connect it and it will recognize it and dump it across the fixture at different frequencies and different voltages. Yes, sir.
Is it code compliant?
Is it what?
Code compliant.
Yes, to run them this way. Yeah, absolutely. You can run them with neutral, without neutral. They're a load. Yeah. A lot of us are not familiar with these. Where would you do an application like this? Parking lot is a good application for it because you can push a 480. Now that voltage 480 all the way across the end of the parking lot, pick a lot of lights at 480. Okay, so here's all the way up to 600. Where's 600 voltage? They use them in tunnels, guys. If you look at the tunnels, Lowry Tunnel and all these tunnels, the light that you do them, a lot of lights in tunnels are running a 600 volt. They bring a 600 volt, 2 phases, and feed, well, 3 phases as a matter of fact, and they scatter the lights right between the phases. Look how efficient that would be. If that was 500 watt, 500 watt, 500 watt, you get yourself a 3-phase lighting system, balanced. So, okay. So that's your voltage. The second thing, guys, is the watts. You can get them, oh man, you can get from 5 watts all the way to thousands of watts fixtures. Literally thousands. I threw here 3,000 watts fixtures, big fat fixtures in terms of watts. Lumens, you can have from 300 to 6,000. These are for fluorescent. If you have a floodlight, the one that they use in the highways and all this good stuff in the intersection, guys, you can have 15,000 lumens coming out of one fixture. Thousands and thousands floodlights for stadiums and sport arenas and so forth. You can have thousands and thousands of lumens. A lumen, the more light the fixture can give you. Any question, guys, about this? The lumens, the light, and these are all, don't hold me accountable to these numbers, just average numbers. Again, I put 6,000 here for basically the lumen like above your head, the troppers. But if you have a floodlight, count on 10, 20, 25,000 lumens coming out of that baby. Okay, temperature. Yes, sir.
Because the number of stores determine the magnitude of the lumen.
The number of
Does it determine the magnitude of the lumen get from
no.
the number of lamps?
Yeah, the lamp in the fixture determine how many lumens you can get by manufacturer. You can't change it. So if I want a 3,000 lamp, I can put a 3,000 lamp in this fixture, or a 4,000, I'm sorry, I can put a 3,000 lumen in this fixture, or a 2,000 lumen, or a 4,000 lumen. There's a limitation, of course. So the lumen goes with the lamp, not with the fixture, to a limit. Now, can I put a 15,000 lumen in this fixture? No, they don't make them. You know what I mean? There's limitation where how high you can go. I was showing Chris yesterday how the fixture that you guys have in visual, you can change the lumen in the lamps. I've been told not to mess around too much with these, but you can go to the lamp itself and change the lumens from 2,500 into 4,000 and so forth. And by adding more lumens, what do? You get more lights, you get more foot candles, you get better, I guess better foot candle, maybe, depends. Okay, temperature. Now, there's nothing better than Minnesota to talk about temperatures. You can go, a lot of them guys are go from minus 20 Celsius. These are Celsius degrees, not Fahrenheit. These are so in Fahrenheit, these are 50 Celsius. Gosh, what's how 50 Celsius? 50 Celsius to probably 200 something Fahrenheit. So it's a lot of and minus 20 Celsius is very cold in the 60s, I believe, almost in the 60s. We can do the conversion here. Have a calculator, but these are the temperature goes. Obviously, the fluorescent lights are not encouraged a lot in a cold location, but you can get the ballast in a lot of temperatures. There's something called, this is on you're going to be tested on this. It's called VCP, a term that they use for every fixture has a VCP. So Oladipo, what's your VCP? You're going to ask, what is the VCP of this fixture? VCP is called Visual Comfort Probability. They put Ashley and 30 of Ashley and Tau people under one fixture, and they survey them. They say, how do you guys feel under this fixture? And they get the data, accumulating, and give it a percentage. So I feel really good under this fixture. Give it 100%. I feel miserable under this fixture. My feelings are completely hurt. My eyes are irritated and so forth. They give it 0. So when you have a fixture, guys, they give it a 0, very uncomfortable to be underneath it, and 100% very comfortable. Does that make sense? From 0, very uncomfortable, and into 100%, which is very comfortable. And most of the fixture lie in between, 80% comfort probability, 90%. The higher the comfort, the VCP of a fixture, the better the fixture, meaning the highest percentage of people feel good under this fixture. Make sense? So that's remember that VCP for every fixture. The last thing I'm going to talk about, guys, in this chapter, talk about mounting. In our project, mounting fixture, you can mount them recessed, right above your head. If it's direct, indirect light, or direct light, completely indirect light. If it's indirect light or direct indirect light, 99.99% of the time you're suspending it. You can suspend it with chains. So you can have it recessed. You can hang it. You can have it surface mounted right on the wall. These are recessed in the false ceiling. You can suspend it, or you can recessed, hung, or you can surface mount it. Typically, these are the methods of mounting them. If you're in a parking lot, you have two options. Outdoor, you can either mount it on a wall of the building, like perimeters, like we did, or you have to create your own structure. What would be the cheapest structure to create to put a fixture outdoor? Poles. What? Balloons. Any question, guys, about this? This is basically what this chapter is all about. Any comments? Any questions? These are, I believe, the most important things that I would like you guys to know from this chapter. There's now moving on, guys. You're going to have at the end of chapter 3, you're going to have something called. If you can do me a favor, if you can go to page, please, to page 33. 33. We're going to talk about the ISO foot candle curves. Thanks God we have ISO foot candle curves, guys. Thanks God we have all these fixtures, and they come with the different ISO foot candle curves. But it will tell you at different heights, mounting heights. Each one, if I'm putting my fixture in this location, these are all ISO foot candle curves. This is what you guys were drawing. Remember when you were drawing when we were in the parking lot, and we said these curves represent all the points that have the same foot candle. So this is what you're looking at. So I'm just picking this one. Right here's my fixture is right here. Right at this point, this curve is 5 foot candle. This curve is 2.5. This curve is 0.5, and this curve is 0.25. And the fixture is located right here. And the distance that we do, this is, they call it, this is, let's just say -1, -2, -3, minus, what do you say, -1, -2, -4. And this point is going to be +1, +2, +3, +4. Okay? And these numbers, guys, these numbers are coming from something, they call it distance to mounting height. Distance to mounting height. The percentage of distance to mounting height. The percentage of distance to mounting height. So take this. If this was if this was a 30 foot, look at this where I am right now here, guys. If this is a 30 foot pole, 1 means 30 feet away from it. Curve in every direction, I'm going to have 0.4 candle, up this direction or that direction. This one 2 times 30, 60 feet away. This one 3 times 30, 120 feet away. And this one will be 4 times 30, whatever is there, 4 times 3, 100, 4 times 3 is 120. So these numbers are multipliers of the height of the fixture. So if I have a fixture like this is very important. Here's my fixture. And the height, this is my mounting height. These isofoot candle will represent mounting height. And would represent the distance. And this one, so right at this point, here's my -1. Right in here, guys, is my +1. So if this, Chris, suppose that this is 30 foot. 30 foot, then from here, point 1 is 30 feet and 30 feet at this point. If it's 2, that will be 60 feet this way, 60 feet this way. That's the amount of light that's going to hit the surface. This is very, very important to understand the isofoot candle curve, guys. That's what you were asking about when we were doing the visual. They take all these lumens, they throw them right at the surface, guys, and they do the calculation, and they connect all the points, they have the same connection, all the points, they have the same value, they connect them with a curve, and they call this curve isofoot candle curve. So here's my question for you guys. Rob, my friend, if I draw another line here, do you think the value is going to be less or more than 0.25? Another line right here, another curve. I'm further away from the fixture. The foot candle will go smaller. Can you guys see that closer you get to the fixture, the more light you're going to get? Makes sense, common sense, right? Any question, guys, about the isofoot candle? Thanks God to AGI and visual. We don't have to redraw this business. They come when you guys do, we did them for the parking lot, but it's the same thing. If you guys go for the fixtures indoor, the indoor fixture that we use, and you pick the isofoot candle curve for them, it will show the isofoot candle for every single fixture. It will be a mess indoor. We use them more outdoor than indoor. Any question, guys, about the isofoot candle? These numbers are a ratio between the distance away from the fixture divided by the mounting height of the fixture. The mounting height of the fixture. Any question, guys, about this? I want everybody, this particular concept, because we're going to do a calculation on this. This particular concept, I want everybody to understand it. Isofoot candle, a curve that connects all the points that have the same foot candle value. The same foot. What's a foot candle? Certain amount of lumen on a certain amount of area. Any question, guys, about the isofoot candle? The second thing I'm going to show you, and these are all in your graph, photometric characteristics. There's some curve. Again, these are drawn in page 33, guys, for you. I'm just going to draw one little curve here. Photometric characteristics. If you put a lighting fixture in this area, and you're going to draw, it's going to draw a photometric characteristics. It's going to have a photometric characteristics that looks something like this. Okay, and these are 180 degrees here, and there's let's draw a whole circle around it. A whole circle around it. Okay, look how nice my circle is. A fat circle from the bottom. Okay, so you can imagine that circle is really good. And this one is 90 degrees. Don't ask me why they put the 180 down. And this is 0. If you put your fixture right here with a reflector, this is the amount of lumens that fixture is going to be giving at that particular angle, at that particular height. This particular one, guys, this graphic, and I'm showing both sides, and then you can have angles. This is really interesting because it gets you all these angles. You can find the angles at different, the lumens at different angles. Lumens at different angles. There you go. So, and I'm going to just pick between, I'm just going to pick, how many do I have here? 1, 2, 3, 4. I'm going to pick 15 degree, 30 degree, 45 degree, and just 80 degree randomly. okay? And I'm picking this. This is a 0. These are the angles. And at these particular angles, guys, it gets you the lumen. Let's write the name of this one. This is called photometric metric characteristics. Characteristics curve. When you drop this curve, guys, on a foot candle of an area, you get your iso foot candle. Who cares? Let's get you these values. This is the values that we're going to be calculating in a few seconds here, guys. So let's say at 15, at angle 15, here's my angle 15 right in here. Angle 15, the lumens at angle 15 is 805. 805. Okay, I picked another 30. Do I have 30? I don't have 30. This is 45. At 45, 1203. At 45, at 1203 lumens. And at 80, do I have an 80? No, I have 90. At 90, it's 3105. At 90, right here, it's 3105 lumens. The numbers that I drew in green, these are the amount of lumens that this fixture will deliver at that height, at that location, at that angle. Thanks God we don't mess with these. Yesterday you were looking at the data. Remember, Chris, when you pulled the data out of it? This is the data that you get. Every single fixture by manufacturer have to come up with this photometric characteristic curve that will tell you how much lumens can come out of how many out of this fixture at that particular angle, at that particular height. The one that you guys are looking at, what is it? The mounting height is, believe it's put at 10. It's candela power value shown or for 150 lamp, for 70 watt lamp. Okay, for 150 lamp with a guard factor, and it's mounting. I believe it's mounting at 10 feet. So this particular one, the example that we have, it's multiplied. Okay. This is for 150 watt fixture. Was it metal halide? No, high pressure sodium. High pressure sodium. High pressure sodium. I don't want to go too much with it, guys, but when you take this value and you dump it on a square foot of an area, you get yourself the foot candle calculation. So do me a favor. I'm going to give you guys a quick break, and after that, here's what I'm going to do. I'm going to be using this curve to do foot candle calculation, the curve that I drew. So when I asked you, I said, go find me the foot candle at angle 15. You're going to go to the table. At angle 15, at angle 15, the lumens coming out of this picture is what? 805. If I tell you, find me the foot candle at angle 45 from the fixture, when there's a formula we're going to be using. You're going to find the lumens that imitated out of this fixture at angle 45 is 1203. At 90 degree, 105. What is it? 3105. 3105. Any question, guys? Any question about these fixtures? Thanks God we don't do it by hand. In the past, Chris, they used to put all these curves together and do the calculation by hand. It's tedious. Right now, guys, with Visual and Lithonia, all this information is embedded into the software, and the only one that we can redraw them when we take the values that I showed you, when we dump them on an area, it gives you the iso foot candle curve that you're looking at. It does calculate it for you. So when we come in a second, guys, I'm going to be taking a fixture like this, and we're going to do a calculation by hand at different points around this fixture. At different points around this fixture. Different points around this fixture. Okay, just to remind you, this curve is a function of the type of the fixture and the height of the fixture they're going to be mounting the fixture at. There's also the guard factor. They have a guard factor and so forth. We'll talk about this one in a second. The last thing I want any question, guys, about this photometric curves and iso foot candle curve? Photometric curves is lumen curve, just lumens, pure lumens at different angles. Iso foot candle curve is foot candle at different distances from the fixture, which is basically they take this one and they put it right at the top of of the square foot of the area with some calculation. So without the photometric characteristic curves, you cannot come up with, without this curve, you cannot come up with the isofoot candle curve. You can't. We went to Ohio one time, guys, to Lithonia factory. You'll be shocked. You know what they do? They have a place in their labs where they put a fixture in one corner and they shoot and they do the calculation at every angle in that lab to calculate these foot candle, 805 and so forth. And so whenever they manufacture a fixture, they take it to the test and they test it. They put it in one corner in a huge room, and it shoots in 3-dimension light, and they go calculate the lumen at every angle, and the room has all the measurement that you can imagine, and they pick up every single angle and they measure the lumens, and then based on the data in the lab, they draw a curve that's called the photometric characteristic curve for every single fixture. Actually, if I change the lamp type or if I change the lamp watt, it will completely change the isofoot curve of this, the photometric characteristic curve of this fixture. Any question? So what I want you guys to do is, when we come back, we're going to do calculation for this particular example. But before I let you go, I want you to look at very important in page 34, please. If you look at page 34, if you guys look at page 34, everybody's looking at page 34. Ashley, my friend, and Tao, you guys looking at page 34? Okay. Put you on the spot here. Okay. Good. If you look at page 34, this is very, the way at the bottom is fig 3.8. These are very important ways of the fixture can shoot light. Let's start with the first one. It says direct. If it's direct, Philip, this is right above your head. That's exactly that fixture, right above your head. If it says direct, meaning 90% to 100% of the light that comes out of the fixture, where does it go? Right above your head. Only 10% go somewhere else. Up to 10% can go somewhere else. That's complete, that's direct. Go the one right next to it, the one that says semi-direct. The semi-direct one, up to 60% can go down, and up to 40% can go up. So that guy shoots a little bit up, so it lets the ceiling too. They call them semi-direct. But look at the percentage though. It can go up to 60-40, 60 down, 40 up. It's still, that's the one that you shoot, that you want to lit the floor. The third one, guys, is called general diffuser. General diffuser, that baby shoots all around it, right? That's, you can put it right in the ones that, as you come to Dunwoody, the ones right at the top of the pole, guys, right here, and it shoots a light right around it. That's a typical general diffuser light. General diffuser in all dimension. The direct, indirect, can you guys see the direct, indirect? Almost 50-50. Almost 50-50, right? It says 40 to 60 in either one of them. I can make 60%, 50% of the light goes up to lit the ceiling, bounce off the ceiling into the floor, and the rest, the other 50 goes directly to the floor. Why would they do something like this? Why would they light the ceiling, guys? It makes people feel comfortable if the ceiling is lit. When we go to Davis & Associates and they walk you through their labs next quarter, you're going to see how they turn certain lights on and make you look the difference between the ceiling. Look at the ceiling is dark right now. But if you have a direct indirect light, the ceiling will be completely lit. It makes people feel more welcome, nice, feel better. Lighting is a big deal in architectural. We fight with architects all the time over light. As a matter of fact, most of engineered projects are done by architects. The lighting are picked by architects, especially the high-profile lighting systems. Okay, direct indirect light. The second one is semi-indirect. Look at the semi-indirect. Most of the light goes up. Most of the light, up to 90% goes up, right? And can be up to 40% guys go down. But the majority of the light goes up. Now, when it goes up, Rob, what happened when the light goes up? It will be bounced down back to off the ceiling, down to the floor. And the last one is the one indirect, complete indirect. This is the one there's no holes. When they put the lamps, guys, nothing, no holes here. Direct, indirect, there'll be holes here. They put the lamp right here, and underneath it is the reflector, and the lamp will shoot almost all the light up to the ceiling. What happens when you have to suspend it though? When you suspend it 2 feet like we did in the conference room, it shoots the light up to the ceiling. What happens to it when it hits the ceiling? Bounce off the ceiling down to the floor. This is the best, supposedly, a complete indirect light is the best light that makes people feel comfortable. You walk into a room which is lit by indirect light, all the light goes up, bounce off the ceiling, so soft, everything is diffused so good, and so forth. That's as far as you guys are going to learn about lighting from a registered engineer, electrical engineer. Any question guys about these? These types of lights are very, very important if you're going to go branch into this arena. Okay, why don't we have 5 minutes break, and then when we come back, I'm going to do calculation based on the foot candle calculation, my friends. What I was hoping, guys, is with these 3 chapters that we covered, we know what the nature of light, the visible spectrum. We talked about the type of fixture lights that we do, the type of fixtures that we use, and isofoot candle curves, and the photometric characteristic curve. These are very important. Now we're going to take all this knowledge, Ashley, and do calculation by hand. We're going to do foot candle calculation by hand. Thanks God we have softwares though. Okay. When we do foot candle calculation by hand, guys, there are 2 methods. There are 2 methods they have to be very, very aware of. 2 methods they have to be very aware of. Method number 1 is the Lumen method. Remember that poor man's job method that we did? The Lumen method? The Lumen method is an average method for the most part. It gives you an average. In the software, it gives you more than an average. But it's supposed to give you mostly an average. No maximum, no minimum, no ratio between max and minimum, minimum to max, and so forth. So here's in chapter 4, here's an example. Take this. The Lumen, there are 2 methods. One method is called the Lumen method or the average method. The average method only gives you the average. The second method, guys, is called point-to-point method. This is the rich man or woman's job or work. It gives you calculation for every single point in your plant. Average method, you're looking at it. If you want to find how many luminaires you need to fit, I have an example for you guys here using the Lumen method. An example using the Lumen method. Okay? The Lumen, the average method. Lumen average method. I have a 60 by 50 room 60 by 50, right? 60 by 50. And I want to know how many luminaires, how many fixtures do I need in this room? Given the following. I need to maintain a foot candle of 80, average foot candle of 80. I need the area is, oops. Don't let me go check the calculation. Did we do it on 50 by, we did it on 60 by 50. Okay, never mind. The area is, oops. The area is, what we say, 50 by 60. So the area is 50 by 60. You're looking at it right here. The lamps, I have a 3-lamper. I'm going to use this one right above your head. The 3-lamper, right? The lumens that are coming out of every lamp is 3,000 lumens. I bought a 3,000 lumen T8 lamps. And the coefficient of utilization for this room and fixture, don't ask me what the coefficient of utilization yet. We will calculate this one. It's given for this application, coefficient of utilization as 0.7. And the maintenance factor, MF, that baby here, it's called MF factor. The maintenance factor is 0.98. And we will calculate what the maintenance factor is. It's a derating factor. Okay? Cool? Everybody knows what I have a foot candle of 80. The area is 50 by 60. The lamps are 3 lampers. And lumens are 300. Coefficient of utilization 0.7. And maintenance factor is 0.98. And I need to find how many fixtures, troffers, 2 by 4, like that one above your head, 3 lampers, 3 lamps in it, I can fit in this room. How many do I need? That's how they use the average method. The average method can give you the foot candle or can give you how many fixtures. If you know what the foot candle is, 99% as engineers and designers, guys, 99% of the time, we are asked to come up with the number of fixtures that we need, right? Nobody asks us what's the foot candle. If I put all these fixtures, what's the foot candle? It could be 10%, but 90% of the time, we're asked to find how many fixtures of this type do I need in this location, right? Okay, so I single-handedly, Mr. Curtin, decided to use the Lambers. Here's the fixture that I'm using. It's a 2x4 fixture, and it has 1 lamp, 2 lamp, 3 lamp. This is the fixture I decided to use. Don't ask me why. Most common, cheapest, most affordable fixture. Okay, so here's the formula. The formula is straightforward, guys. The number of fixtures, the luminaires, equal the foot candle multiplied by the area, divided by the lamps, how many lamps, divided by how many lumens, divided by the coefficient of utilization, divided by the maintenance factor. On the test, bring the formula with you, if you don't want to memorize it. Okay? All right, so let's go apply it. What's the foot candle? What's the foot candle that I need to maintain this room? 80. What's the area of this room? I think I'm doing an example. I think this calculation is based on 20 by 30. Let's do it by 20 by 30, guys. I'm sorry. Let's do it based on 20 by 30. Because the calculation is done. Is it? Then the dimension here will be 20 by 30. I think one of us was drunk that day. 20 by 30. It doesn't matter where you put the 20 and the 30. Okay? So I put the 20 by 30. If you do the area divided by 3 lamps, where did the 3 lamps came to be? I decided I'm going to use 3 lamps. Ashley wants 4. Put 4. If you don't know, by the way, where's your start point? 3. How many lumens? 3,000. That's your start point. Divide by 0.7, coefficient of utilization. How much of the light is going to be utilized where I need it to be utilized? Divided by 0.98, the maintenance factor. Maintenance, I'll tell you what the maintenance factor is in a second, guys. When you add all these values together, how many fixtures do you need in this room? How many fixtures do you need in this room? By the way, if you end up with 38.5 or 38.4, how many fixtures do you need? You can't have 0.4 of a fixture. It's always up. Any fraction is always up. Is that calculation right, Chris? The man?
One of us is wrong.
Okay, well, anybody can verify the calculation, please? I don't know. 80 times 20 times 30 equals divided by 3 times 300 times 0.7 times 0.98, close it, equal. I have 77 here.
7.7.
77 lights would be a lot of.
What did you guys come up with?
7.7.
Based on the 30 by 30?
Right.
Okay. 7.7, that will give me how many? 8, thank you. That will give me, I'm going to say 7.7, and that will be an 8 fixtures. Thank you. So I need 8 fixtures. I think it was based on the, okay, well, just based on this calculation. 8 fixtures. Cool? 8 fixtures. Any question, guys, about this formula? Now, if I go here and I change this to 2 lamps, and I change the lumens to 4,000, and change coefficient of utilization to 0.8, and change the maintenance factor to 0.7. Can you do the calculation, find how many fixtures you need? Piece of cake. Can I have a thumbs up that, Chad? We know that. We hammered it. It's really good. Okay. So that's a calculation. That's called the poor man's job calculation. This method, you have to know, guys, the type of, every method that you do, you have to know the type of fixture that you're using. You have to know the type of fixture. Does it have to be 2x4 and lamps and all this stuff? Could I use round fixtures, cans? Yep, you can use cans. Instead of number of lamps, you can have, the cans can have 1 or 2 or 3 lamps. Some cans have multiple lamps. Does it have to be 2x4? Any question, guys, about this? Any question? Cool? Everybody's okay with the calculation? So, okay. The second thing I want to do, and then, of course, this calculation is wrong. I'm going to go erase it immediately and do the calculation with you. How to place these fixtures. I know who asked me. Oladipo, my friend, you were asking me how to place these fixtures, right? Since you know them now, how do you place them? How do you place them? Where do you start? Where do you start placing these fixtures? Let me give you a rule of thumb here. Okay, so I want to remind you, what was the area? 30 by 40, right? We have a 30. How did they play? How did they orient it?
20 by 30.
It's 20 by 30. Okay. We oriented them 20 by 30. Okay, here's my 20 by 30. Here's my 30 feet. Here's my 20 feet. Okay? How many fixtures do I have? How many fixtures? 8 fixtures. Now here's what I would do. Find the two numbers that you multiply by each other to get you 8. The largest two numbers that you multiply by each other to get 8. What's your option? What's your option? Your option is 1 by 8, 2 by 4. What else? Do you have any other option? To get 8? So why am I doing it this way? This will give you how many rows and columns you need. How many rows and how many columns you need. Because eventually you need rows and columns. So I can have either 1 column and 8 rows. That would be nasty. Or I can have 2 columns and 4 rows. Now the larger number goes towards the larger side. Okay? Everybody knows what I did here? Take the number of fixtures and try to find. Now what happens if I have 7? Oops. What I do, because this is an average poor man's job, guys, what I would do, remember, this is average method. Make them 8 and do your calculation. Make him even number. Make him a number that you can multiply 2 numbers together. That's what I would do.
Make a grid, right?
Yeah, you're going to make a grid. Thank you. We're making a grid. Okay, so I'm going to use, for this layout, I'm going to use the 2 by 4. By the way, the more rows and columns you have in a building, the better distribution your system would be. So the number 4, so I need 1, 2, 3, 4. Here's 1, 2, 3, 4, right? Here's 1, 2, 3, 4. 4 columns. I have 4 columns. Why did I choose the columns to go with the 30? The largest number actually goes with the largest dimension. The largest number goes with the largest dimension. Now, if the 4 went with the 30, where do you guys think the 2 is going to go with? The 2 is going to go with the lower one. So here's 1 all the way. Do I have 2 rows? I have 2 rows and 3 columns. That's your start point. 2 rows and 3 columns. Any question, guys, why I came up with 2 rows and 3 columns? My option was 1 row, 8 columns. That would be nasty. So you choose the number that's the closest to each other, like 2 and 4 closer to each other than 1 and 8. Okay? Remember, this is an average method. An average method. If you don't have a software, you don't have a software. Cool? All right. So at this point, we know how many we need. Then we need to divide it, this area. Here's what I would do. I need to divide this area, guys, into x's and y's. This is x, 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 and these are y's, y's. Okay? I need to find the distances, right? So take the x's. How many x's do I have? 4 x's equal what? 30. And you guys know the math. What's 30 divided by 4? 30 divided by 4 equal 7.5. So x equal 7.5, right? Did you do it right? Or my calculator is dead. 7.5. Let's do the y's. The y's. How many y's do I have? 2y equal, what's the dimension there? 20. So y equal what? Equal 10. What? Did somebody telling you to mislead me today? Any question, guys, why I found the x's and the y's so I know what the dimension of that picture is going to be, right? And then, my friends, you're going to go put your fixtures. You're going to put your fixtures in the middle of that baby here. So right in the middle. So right here, you're going to center it right in the middle. 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. Okay, makes sense? Right in the center of every of these rectangles. Now, since we know I need to identify the location, so when I send the electrician to go install that fixture, I need to identify the center of that fixture. And then you can identify the sides too. The center of the fixture, guys, right in here. Okay, I want to identify the first fixture, the first center. You guys agree with me if this is, what was it, 7.5? From here to here is half of it, right? Right? If this is, this area here would be 7.5 divided by 2, right? Or this is my, no, my y is 10. My y is 10. This is a y going down. So this is will be 10 divided by 2. That will give me what? 5. This is, so I'm going to go 5 feet from here. Now that's the vertical. I need the horizontal. The horizontal, let's do the horizontal. The horizontal right here, it's going to be 7.5 divided by 2. Again, what would that give me? How much? 3.75. So that would be 3.75 equal 3.7575 feet. So this area would be, these are the dimension that I'm going to give to the electricians to go install it. Now, these are, some of them are hard, so you have to use your judgment sometimes. So the first fixture will be, the X for the first fixture, 3.75, and the Y for the first fixture will be 5. Any question guys about that? If I find the X and the Y, can I grid the rest of them? Piece of cake, Chad. Then that's what I'm going to be asking you guys to find the first fixture, then the rest of them are piece of cake. Then if I ask you what's the distance here between these two? Right? What's the distance between these two? Well, this is half of an X and this is half of an X together. That will be what? An X. What was the X? How much? 7.5. So they're going to be at 7.5, right? 7.5 here. Let's go the distance between these two centers, center to center. This is half of a Y and this is half of a Y. The distance is what? Half of Y and half of Y is a Y is 10. 10. That's it. I identified the first fixture and the second two fixture next to it. Then can I grid the whole thing, do the measurement in between them? Piece of cake. All of them are going to be gridded at 7.5 horizontal and 10 vertical. Done. Any question? Any question, guys? Yes, sir.
Why did we divide by 2 for the X?
Why didn't we divide by 2 for the X? Oh, because the whole area here is an X. If you want just the center of the fixture, it's a half an X because you're centering the fixture in the middle of the square or rectangle. This side is X. This center of this fixture is going to be right in the middle of that side, which is the half of the X. And the same thing, the half of X and half of a Y. Okay? Now, if you guys end up with 50 fixtures, would it be different? You try to find two numbers that you multiply to get you 50. That will be 10 by 5. Can I get anything other than 10 by 5 for 50? What? Remember, you're going to get, that's a good point, but 25 by 2, there's way far away from, you need these two numbers, guys, to be as close to each other as possible. When you factor in numbers. That will give you the best distribution. Any question? Can I have a thumbs up? Yep, now we know how to do it, Chad.
For geometry's sake, are you using X as vertical then?
Am I using X as vertical? No, here I'm using X as horizontal, and Y is vertical.
So you say you're going down 7.5 feet?
I'm going this way, 7.5.
Oh, okay.
Yeah.
Oh,
Yeah, the X are the horizontal, and the Y are the vertical, based on what I did. Any question, guys? That's how you place your fixture. Now, these are 2x4 fixtures. Had they been a can fixture, would it be different? If they were the reason why I like how to use the grid XY, because if they are cans, the same application. Had they been cans, you know what you're going to do? You're going to put a can here, right in the center. Right? That's it, if they were cans. If they're square, rectangle, whatever shape they are, if you can capture the center of the fixture, then you can capture the whole thing. A lot of people, guys, go to the edge of the fixture here. Well, it's great, but if it was a different fixture, if it was a round fixture, then that wouldn't get you anywhere. That will cover all the cases, regardless of the shape of the fixture. Can I have thumbs up, Chad? We got it. We know how to place them by hand. When you guys do it in Revit and Visual, keep this in your mind too. That will give you kind of the distribution. Now again, Nick, you did a great job. I think you and Chris when you place your lighting fixture over the tables. This is general distribution. Now, if my tables are lined up this way, I might have to go and realign my fixtures over my tables. That's assuming I have no idea what's going to be in this room, which is most of the case. We really don't know where the tables are going to be when we walk in. We just line up our fixtures. That's the best way to do it. Any question, guys? Piece of cake, not a big deal. Not a big deal. So with this one, so now this is definitely will be on one of our tests, guys, where you can find the number of fixtures and place them in a room. And I always, now what happens if your room is not, what happens if your room is a square? A square is easy. What happens if it's a rectangle or if it's a other shape? It gets more complicated. What I usually do in this poor man's job, if you have a circle, guys, just make it close to a rectangle. You know, you can do approximation. Approximate things always to a rectangle or a square, always. And then do your calculation. Then when you go back to real application, you might have to shift things around a little bit. Am I clear about this, guys? Can I have thumbs up, thumbs down? Good. Okay, so that's what I wanted to. I wish I was able to do that before we did the visual, but you know, it is what it is. Okay, now the rest of it is what remember that there was something called maintenance factor. Now what the heck is a maintenance factor, Chad? Remember that boy here that I gave you and you guys all accepted it and nobody asked me what the heck is that maintenance factor, right? Now we're gonna go, the book talks about calculating that factor. Okay, so let's go quick about maintenance. It's called MF, maintenance factor. This factor is a function of multiple other factors. And you really don't have to worry about it, guys, because usually you get this number from the fixture and the application. But how to calculate it if you have to? It's DDF, LMF, LLD, and TF. Now what the heck is that, Chad? Right? You know, MF equal DDF, LMF, LLD, and TF. Here's the definition of each one of them, directly from your book. DDF stands for dirt depreciation factor, how dirty you are. If you are a kid like Chad, grew up on a farm, your DDF would be probably 50. If you're a city slicker like Chris, still grew up in the cities, you're probably close to the 90. Oops, is that stereotyping? No? No stereotyping here. So the dirt depreciation factor, it really goes by the location. A room that's, if the location is dirty location, the dirt depreciation factor will be small, dirty, like 0.5. If you have a hospital, for example, it's clean location. Offices, relatively clean location, that will be in the 90s. Everybody knows that? What the dirt depreciation factor is? You have to use your judgment on that one. So dirty is 0, very dirty, clean is 100. Okay, then the second one is LMF, lab mortality factor. Lab mortality factor, when they design them, guys, each one of them have an LLMF. How fast it's going to die? Everybody's going to die. All of us are going to die. The lamps are going to die. How fast it's going to die on you, based on manufacturing of that fixture. That's by manufacturing. And so that factor is a function of how often do you relamp. Do you relamp every 2 years or every 10 years, right? If you relamp, everybody knows what relamping is. When you take multiple lamps and you ask one of your electricians to go and take every single bulb in your fixture out and put new one. That's called relamping. If you no relamping, you don't relamp at all, it's very close to 0. If you relamp more often, every 2 years, every year, every 3 years, you're close to 100%. Okay, cool? The second one? Huh?
Which one is better?
Which one? By the way, the higher the number, the better. In all of these factors, the higher the number, the better. Everybody knows that? The higher the number, percentage-wise, the better application for you.
So you want to relamp a lot?
You want to relamp more often? Not a lot. You have to find the happy medium between spending the money. But if you don't, if you put a bulb like this and you let it sit there until it dies in 4 years, that's not a good idea. I can't remember what is it, 2 years or 3 years. Every 2 3 years they relamp. A lot of companies relamp every single lamp with your fixtures. Okay. Any question about DDF, guys, and LMF? Quick. Okay, I'm going to go to the second one. LLD, lamp lumen depreciation factor. It's called lamp lumen depreciation factor. I need to go. Lamp lumen depreciation factor is, guys, this lamp is giving you 3,000 amp day one, 3,000 lumens day one. Do you think 24,000 hours is going to give you the same amount of lumen? Absolutely not. So this is a factor from the manufacturers. Zero. The lamp, no lamp has a zero depreciation factor, guys. It's going to be close to the 80s and the 90s. How good the lamp can maintain the lumens over the time. Manufacturer factor assigned to the lamp. You get it from manufacturer. The last one is temperature factor. Temperature factor. There's a temperature factor. There's a graphic in your book, guys. That factor comes from a graphic. Change in lamps, lumen variation. Where did that? There's a factor. Where are we getting to? So if your temperature is different, you have to adjust your factor. Where is it? Change in lamp variation, voltage, temperature. Temperature factor. It's in page 42. If you look at 100% of the lumens happen at 60% temperature in degrees Fahrenheit. 60% give you the best temperature, best lumens. If you go to 100, look at how. Can you guys? Everybody can see that curve. There is an ideal temperature for the lamp to give you the best lumen. After that ideal temperature, if you go lower or higher, it gives you less. So this factor, this will be translated to a factor. Like for example, if you're running at 20, and these are Fahrenheit, then you have the percentage of lumens is 0.4. Your temperature is 0.4. Okay, so that's another factor. When you guys put all these factors together, before I do my calculation, you put all these factors together, Chris, you're going to end up with the maintenance MF, the maintenance factor. Any question? As far as you guys are concerned, these factors, either you judge them or you can come up with a lump sum factor and say, you know what, I want to approximate this one into 0.9 and call it a day. Questions? Okay, so I want to continue, guys, when I come with the calculation now. Do two examples, but I have to go for a second here. So take a quick break. All right. So any question, guys, about what we covered? The lumen method. Now, as I said, if I can have your attention, guys, we're cool, right? So we have two methods. We did the lumen method. We did the calculation based on the fixtures. We can also do the calculation based on the foot candle. If you guys remember the formula, number of fixtures, if you put the number of fixture here, if you put the foot candle here and the number of fixture underneath, you can calculate the foot candle. Either way. This method here, guys, is basically to calculate the foot candle, not the number of fixtures. You have your fixture and you need to calculate the foot candle. Okay, let's just look at the example that we have that we're going to be using. Let's see. We're going to look at the example that we're using, guys, so we can be all on the same page. All the same page here. Okay, so let's look at my foot candle. All right. So if this method is the second method that we said, and it's called the point-to-point method. What's the advantage of this one over the lumen method? It gives you every single foot candle at every single point in your surface versus the average foot candle that we used in the example before. That was average. So it gives you every single foot candle. From that, you can derive the average. You can derive the maximum. You can derive the minimum. You can derive the max to minimum, average to minimum, and so forth. Why is it important, guys, for us to do the point-to-point method? Because point-to-point method gives you the average, which is good, but also gives you the max to minimum, which is the ratio between the brightest bulb on the tree and the darkest, dimmest bulb on the tree. And that's very important for us, Dustin, my friend, because we can it makes our eyes look comfortable. If you're looking at an area where there's good lighting distribution, meaning the maximum foot candle and the minimum are close to each other, that will make you feel good when you look in this room, right? I asked you guys before, if you walk into a room and one corner is completely dark and one corner is completely lit, wouldn't that make you feel uncomfortable? No? Oladipo? Just say yes for me. For this one, no? Okay, so this point is supposed to solve the problem of distribution of light. Okay, give you the maximum minimum. The rules are very easy, very simple. This applies, at this point, applies only for outdoor lights, but you can apply for indoor light. Take the example I'm having. I have a high pressure sodium, 150. It's 150 watt high pressure sodium. The height of this fixture is 10. The height of the fixture is 10. And I will do the calculation, find the foot candle out of this high pressure sodium at point 1, which is right underneath the fixture. Okay, you guys with me? Right underneath the fixture. This point is called nadir point, and this has nothing to do with nadir. Rolf Nader. You guys remember that? Is he running for election this year?
No, I think you have to be alive.
Did he die?
No, he's pretty close. Pretty
Oh,
well.
that's what I thought. He didn't die. Okay, this has nothing to do. Nader, I think the name of the guy who invented the point or did the calculation, Nader. That's how I say it anyway. Nadir point right underneath the fixture. Here's the pole. Right underneath the pole is called the nadir point at 0 degree from the vertical.
At horizontal, or is it at
Vertical, right? We take the angle from, here's the angle between the vertical. So when you go down here, this is 0 from the vertical. Okay? So this is at 0 angle nadir point. I will find it also at 3 as well as at 2. At 2 different points. At 2 different points, I need to find the distances. And I'm giving you guys the angle, 45 degree, at 45 degree angle and at 65 degree angle, I need to find the foot candle. The formula is very clear, and please correct your book. It's very clear. You take the formula to find the foot candle distance, you take the candela power, CP here, foot candle, CP stands for candela power. Cosine Q is the angle right here with the vertical. The angle with the vertical. So CP times cosine Q, the angle, divided by the square of the distance. Cool? So that's the formula that you're going to start with. The smarter than Chad, if you use geometry, if you take the cosine, you're not going to do that one, but any question guys about this formula? The CP multiplied by cosine Q divided by the square of the angle, the square of the distance, that will give you the foot candle at this point. You guys remember the isometric characteristic curve, and we said that the lumens are given at different angles? That's what we're going to be picking up at different angles. So this fixture at 45 degree angle is going to be illuminating certain amount of lumens. These lumens are going to hit the surface and giving us certain amount of foot candle. And our job is to find this foot candle. Am I clear what we're doing? We're trying to get a fixture from the manufacturer that has an isometric curve already given, and we need to find the lumens at 2 different angles. We can find them at any angle. And I need to find the foot candle at these 3 points. Okay. Now to simplify the calculation, the smarter than Chad came, and they say instead of measuring always the distance, let's use TREG to simplify this formula. So if you guys look at this is the hypotenuse, right? And these are the 2 right angle. This is a right angle triangle. We all know that right angle triangle, hypotenuse, and 2 sides. From the formula of the right angle triangle, the hypotenuse, right? You can take the cosine of this angle. We're talking about this angle. Cosine of this angle equal the adjacent over the hypotenuse. You guys remember that from the days of high school? Adjacent is H. The hypotenuse is D. This is just what's going to be D1, D2, D3 later on. Just the adjacent over the distance, right? Adjacent H over distance. If you take this formula and plug it here, you flip it and you put HD instead of cosine, and you do the math. Actually, if you flip the D, solve it for D and plug it into this formula, you're going to end up with this formula: CP times cosine Q cubed. Your cubed, yes, raised to the power 3.
No, you have a word that looks like cosine.
Cos?
And then you have an at sign.
Cosine, this is an angle Q.
Oh, okay, so that's the letter Q.
Angle Q, or theta, or whatever you want to call it. The angle Q.
Okay.
Whichever, here's the angle, 45, 65.
No, it's just hard to read it right.
Sorry.
And up above,
Raised to the power 3, multiplied by the maintenance factor. Remember the maintenance factor we just talked about? The maintenance factor? Multiplied by the maintenance factor. Divided by what? The square of the height. The square of the height. Any question, guys, how we went from this formula into this formula? If we're doing horizontal calculation. If you're doing vertical, the formula will be different. I'm only doing horizontal. What's horizontal lumens? Horizontal is coming from this down to the floor, not to the wall. Any question how we went from foot candle equal candela power multiplied by the cosine divided by the square of the distance into candela power multiplied by the cosine raised to the power 3 divided by the square of the height and multiplied by the maintenance factor. Also here, we should have maintenance factor. Maintenance factor is another factor you add at the end. Maintenance factor. Any question about the formula first? Can I have thumbs up that we're good? Yes, no, Ashley, Tao, my friends? Cool? If we test you guys with a quiz after that, will you be able to do it? If I quiz you?
if you look on page 45.
I know it's different in the book. Can you guys add in the book? Can you add it's
the book
Q?
wrong?
Yes. The book in the book, guys. This says cosine squared. This should be cosine cube. And I'm not going to prove it here for you. If you do if you plug in the cosine in the formula D, it should be cosine cube. Cool.
Yeah, they don't even, I mean, they don't have no cosine to any power, they just have CP times cosine.
Yeah. Are you talking about this one here?
Yeah.
Yeah, this one there's no cosine, there's no power here. But when you move it to here, this is when it changes it. Okay. Any question guys so far before we start using the formula?
So is the calculation in the book incorrect, or is it?
It,
The
I want you
book
to
is
use-
over the distance squared, and yours is over the height squared.
when you plug the distance in this one, it will turn it into that formula. I will do it after the class. Would you? We'll prove it.
So I'm just
Okay.
asking you a question, whether yes or no.
Any question about the formula before we go plug in the numbers? Any question about the formula?
Is the CP given?
CP, we'll go in a second and find the CP. We'll go in a second and find the CP for you. The CP. Okay, so let's go. So everybody knows what we're doing, guys. I'm giving you the maintenance factor 90, and I'm giving you the height 10, giving you two angles, and I would like you to find the foot candle at 3 points, at 1, 2, and 3. 1, 2, and 3. At 1, 2, and 3. No, using this formula. Using this formula. Now to find the foot candle, Rob, my friend, at point 1, you need to find the candela power at point 1. This is from the isometric, from the isometric curves of that fixture from the manufacturer. And then you need to find the cosine of Q. In this case, the cosine of Q is 45 if it's 2, and 1 if it's 0 if it's the angle right underneath it, and then divided by square of 10 multiplied by 0.9. Let's go do the first calculation. Any question about what we're supposed to do? We're supposed to find foot candle at 3 points under this fixture. Shall we go ahead and do it? Rob, guys, you're good? Phil? More or less? Okay. All right, let's go here. The first calculation that we need to go, guys, is the point 1. I want to remind you, point 1 calculation is right underneath, and it's called the nadir point, right underneath the fixture. Does that make sense? Right underneath the fixture? So if you go to right underneath the fixture, guys, do you agree with me that the Q under the fixture is 0, right? Because you're taking it with the vertical. The Q is 0. So then if you go to Fig 4.1, page 40, let's go to page 40, guys. Please go to page 40. if you look at this information, I need to find the candela power values for this fixture. If you guys, so that the angle is 0, and then to find the candela power, you need to go to Fig 4.1, page 40 in the book, not the code book, the lighting book. What's the candela power? Can you guys see this little table here at the bottom? Everybody can see this little table. If you guys go look at what's the angle at angle 0. Aladipo, can you read me the candela power at angle 0, please? How much? 650. Everybody knows where the 650 came to be? From the candela power emitted from that fixture at angle 0. At angle 0. Okay, 650. Any question where the 650 came from, please? So to find the 650, you really need to find the angle first. Without the angle, you cannot find the 650. Everybody knows that, where we get that information from. Now, every fixture that God created that's used in the industry is going to have this figure here for it that gives you the lumens at different angles emitted from that fixture. Okay, let's go plug it in. If you find these two, you're done. If you know the angle, and if you know the lumen at the angle, you're done. The rest is just 9th grade math, right? So foot candle multiplied, here is the formula, CP cosine Q to the power 3 divided by square of the distance multiplied by maintenance factor. Okay, CP is 650, right? Are you guys with me where the CP came from? 650 at the angle. Cosine 0, what's a cosine 0? Everybody knows how to use a sine, cosine, tan from the calculator. These are the only thing you need to know, guys, this quarter. Sine, cosine, tan. So cosine 0 is 1. If you don't believe me, put cosine and take the cosine 0 is 1. Multiplied by MF. So then you plug it in, 650 times 1 times 0.9 divided by 100. Where is it the 100 came to be? 10 times 10. Is this number right? Can you check this one for me? I don't know if we multiplied by 0.9 before. I have a feeling that we didn't multiply by 0.9 here. 650 times 0.9 divided by 100.
Right.
Is it right? 5.85, which is 5.9. So, Aladipo, my friend, right underneath the fixture at nadir point, the foot candle is 5.9. Done. The foot candle is 5.9. Any question, guys, at point 1? I want to remind you, we are calculating at point 1. Any question? Phil, does it make sense? Yeah. Back to the drawing. Okay, so where is point 1? Point 1 is right here at this point. Point 1 is right here. Justin, makes sense? Nick, my friend, you guys do that? At Mashad too? No, they don't. They do the softwares. Now again, guys, we're not going to be using this one for our project. We use visual. We're very smart and sharp in using visual and doing the calculation. This will make you understand and appreciate the calculation that the software is doing. Now, we calculated for 1 point. Imagine calculating for hundreds and hundreds of points that the software is doing, based on almost the same principle, with a few modifications because we're doing it indoor. There's reflection. Okay? The only thing that's not taken into consideration in this formula, Rob, my friend, is reflection from the walls and the ceiling and the floors, because there are no walls, ceilings, and floors. These are outdoor fixtures. We're doing calculation on outdoor fixtures. That's the assumption. When we do them indoor, the same method, but we take into consideration two things. Something called direct lighting, direct light, and indirect light. Direct light that's coming from the fixture, and indirect light, the one that's bouncing off the walls, the ceilings, and the floor, and hitting the object that you want to lit. Right now, this is all coming from the direct light. Okay, can I move and finding the 2? Finding 2, everybody? Cool. Can I go find the foot candle at 2? So we found it at 1, we're going to go to 2, and then we're going to go to 3. Okay, piece of cake. Everybody got this info here? Yes? No? Cool? Okay. Foot candle at 2. At point 2, the angle at point 2, Q, doesn't look like Q. Now he's going to be yelling at me here. Here's my beautiful Q. As beautiful as it could be. Q is 45. Why 45? Because I single-handedly, Mr. Kurdi, decided to put it 45. It could be 65 for all practical reasons. 45, right? Given 45. Now tau, my friend, from the fig 4.1, page 40, for that particular fixture, high pressure sodium, 150 watt, right? For that fixture, if you go to that fig, then this table that you're looking right in front of me, you're looking at right here, if you go to 45, can anybody read? Who's going to read for me? 45. What's the foot candle 45? How much? 1203. 1203. Phil, can you guys see it? That from the table? 1203. Okay, so here's 1203. What? Dollars? Or what? Lumens. Thank you. Lumens. So you stick the 1203 in the formula. Cosine 45. Why 45? Because I need the value at 45. Multiplied by 0.9. Don't forget the 0.9 here. So cosine 45 is 0.707. If you don't know that one, you have a calculator in front of you, right? Take cosine 45, 0.747, cube it, raise it to the power 3, then multiply it. You should come up with 3.8. 3.8, right? Audible? Came up with 3.8. Any question guys about this? Any question? Now here's my question for you guys. If I give you any other angle, would it be different? Chris, would it be different, the process, if at any other angle? Straightforward. Straightforward. Any question guys about finding the foot candle at point 2? The foot candle at point 2. I want you guys to look at the foot candle right under the fixture was 5.9. As we move away from the fixture as expected, what happened to the foot candle as you move away from the fixture? It goes down. Makes sense, right? You're moving away from the light source. You're going to get less light. Any question, my friends? Okay, let me know when I can move to the next one. Cool. Okay, let's go to the point 3. Before I move you to point 3, let me go just show you guys where point 3 is located. Point 3 is right here. Point 3 is located at 65-degree angle with the vertical from the fixture. Okay, at 60.
Distances here, or
I don't care about the distances here because
it's a question.
Yeah.
Does that represent the end point, or does that represent a distance?
Which one is the 65?
Number 3 on the left and number 2 on the right.
Number 3 represent just a number, not distance. Not this, just random numbering. Okay, so let's go to number 3. No distance. I see your point. No distance. No multiplying by 3. No distance. Okay, at point 3, Q, Miss Q equals 65 from 4.5 at 40. Dustin, do you have your book handy? What's the value at 65, please? 3,675. So, right, 3,675 right here. And by the way, I added here, Rob, my friend, this fig is actually your IES file in the software. All these figures that we're doing here, it's an IES. When you pull an IES file, that's what you're doing. Okay, so you take this number, 3675, multiply it by cosine 65, use your calculator, cube it, multiply it by 0.9, divided by 100, and you're going to end up with a healthy 2.5 foot candle. 2.5 foot candle. Any question? 2.5 foot candle. Any question, my friends? Any questions? If I give you guys any value at any angle, would you be able to calculate it based on this rule? Should be straightforward, right from the text. When we test you guys on the test 2 and final, what I'm going to be doing, I'm going to give you a graphic like this, a picture of this graphic that you're looking at, and you're going to go to the graphic and get the foot candle at that right angle. Now, what happened if I give you an angle that's not here in this table? Take this. I want to give you guys the angle 20. Look at that. You have 15 and 25. If I give you 20, what would you do? Well, for Chad's calculation, go to the higher, 25. In real calculation, you have to do interpolation. Is that what they call it? Interpolation. Interpolation, am I saying it right, Chris? You have to do interpolation of data. I don't want you to do interpolation of data until you're going to be a certified lighting designer. You have to know how to interpolate. Very easy. If you have two values and you know the correspondent to two values, and you have one value between them, you should be able to find the correspondent to the third value. That's what by the slope method. Okay, for our sake of calculation, when I give you guys, if I give you 20 angle, and you go there, 20 is not there, what are you going to use? Next stop, 25, just to simplify the process without doing interpolation. If anybody's interested in interpolation, we can do it one-on-one. I'm not interested in interpolation at this point. Any question, guys, about this? Any question? So that's piece of cake. Now, the other foot candle, guys, if you have a pocket, so that's basically, that's all the calculation I would like to do on this. If I asked you any other angle right now to do the calculation for it, give you the angle, should be straightforward, no gimmicks. You can do any calculation at that particular angle. But I have to give you two things though. I have to give you the angle and I have to give you a graphic like this in order to pick up the foot candle for it. Otherwise you're doomed. Okay, in a parking lot, if you guys remember when we did the parking lot, here's the fixtures. When you have multiple fixtures in one area, they add each other's up. So for example, look at the green line here. The green line, when they intersect, I have fixture 1, fixture 2, fixture 3, fixture 4. Remember how we were grabbing the iso foot candle of these curves and we put them at the top of each other? Every time you put them at the top of each other, they add each other's up. So take this. If this point here is 0.5 and this curve is 0.5, right at the point of intersection, if there's a 0.5 coming from fixture A and a 0.5 coming from fixture B, what do you guys think the total foot candle would be? They add each other's up. They add each other's up. The same thing. If this point here, I'm going to tell you this point was 1 foot candle and this point was, let's just give you 3 foot candle. Right at the point where they intersect, this curve will give you 3 and this curve will give you 1. What do you think the total would be? Add each other's up. So you're going to have a 3 plus 1 equal 4 foot candle. So anywhere at that point when they intersect, they're going to add each other up. So every time the iso foot candle curves overlap, when they overlap, they're going to add each other's up. So every fixture is going to contribute with certain foot candle to the other fixture at the same location, and you're going to add them up. Any question, guys, about adding the foot candles of two different fixtures from iso foot curve? Iso foot curve. Chris, does it make sense when they overlap them, add up? Well, I'm just using right at the point where they overlap, not in between, just right at that point.
Where is that point?
Right here. The point of intersection.
You can compute that point.
Yes, absolutely, yeah. You're going to do a calculation from fixture at this point, from this fixture at this point. You're absolutely right, and add them up. Yeah. Now the software, thanks God, when you guys were doing it for lighting, our software, Visual, you grab the iso foot candle curve from this fixture. Remember that? And when Andrew was here, and he said you guys have to put them not next to each other, a little bit overlap. What do you think you made a little bit overlap? Because the parameters of the iso foot candle are the least lit area. If you put the least lit area parameter of one fixture with the least lit area of a parameter of another fixture, they add each other up and give you a little bit more light. That makes sense. Any question about this? How you can put two, but like Chris absolutely said, in order to add them up, Chad, I have to either me or the software have to do the calculation at this point from every fixture. As a matter of fact, I have to do the calculation from this fixture to this point. At one point, guys, you're going to see later on when we do other chapters, we start kind of letting go with the, because it's too far. It's irrelevant. We drop it. It's not substantial. They call them irrelevant. If the fixture is way far away from the point that I need the calculation, I mean, you can do the calculation, you end up with 0.0000 foot candle. Does it really make sense to do the whole calculation for a 0.000 foot candle from that fixture at the end? So, now for example, here's what I'm trying to say. If you take the contribution of this fixture here at this point, it will be negligible. It's not worth doing the calculation. But it does though. In order to, if you want to do the exact calculation, you have to, at that point, contribution from fixture A, fixture B, fixture C, and fixture D. 3 foot candle calculation from 3 different fixtures at the same point. That's what the software does. When you guys run visual, it takes a foot candle from every single point. And it adds them up. It adds them up. It adds them up. Okay. The second thing I want you guys to do is they have the ratio. This is where you were talking about the ratio. The ratio, they use the distance along over mounting height in order to get good distribution of any lighting fixture. If you don't have a software, you're gonna take the height of your fixture divided by the distance away from the fixture divided by the height of the fixture will give you 2. That will give you a good distribution. So in my case, if I have a fixture of 10 feet and I want to get good, and if I want to get a good distribution, rule of thumb for a fixture that's mounted at 10 foot. Again, we have the software, so we don't have to worry about this one. But the rule of thumb, to distribute the fixture, you go twice between the fixtures, twice the distance, the height of the fixture. So for example, if my height of my fixture is 10, so my fixture will be good enough for a circle of 10 around it. If my fixture is mounted at 30 feet, my fixture outdoor, say if I have a fixture and this fixture, let's just use this fixture here. This fixture is 30-foot fixture, and I will put this fixture in the parking lot. This fixture will be good enough for a mounting height of 2 to 1, 30 times. So that will be between the fixtures, that will be the mounting height to the ratio. If you multiply 10, that will be 60. 60 and 60 with a mounting height of 2, 60 to 60. And that circle, if you can imagine a circle going all around it, that will give you a good distribution, well, depending on what your minimum is. So on a mounting ratio, so you want you to maintain a mounting ratio of 2 to 1. Distance along.
So is that the radius or the diameter?
This is the distance. Okay, the distance from the fixture is twice the distance, the mounting height. Okay, so the distance would be twice the mounting height. Yep, that would be the radius, based on what we're showing.
The upper is the radius?
And the lower is the radius too.
No, okay, you have a thing that says ratio. And then next to the ratio, you have an equal sign.
Yep.
So you're saying that the ratio is the radius divided by the height?
Or
are you saying the diameter divided by the height?
The radius.
Okay.
The
You
radius.
have a radius of 60.
Radius in this example,
And
if it's
dividing it by a height of 30 in order to get to.
yes, absolutely. In my example here, I have guys 10, so the distance is 20. Where I can actually, this is just to place my fixture. This is for placing my fixture. So if you look at the distance between placing your fixture, so 10 to 1, that will give me 20. The second line I have to put a fixture right here to get a good distribution, right at the end. So after a 60, I have to put another fixture here. And I have my fixture here.
And the 60 based on the numbers you're giving your example here.
You want the distance between your fixtures twice as the height of the fixture. Make sense? The distance.
So the mounting height of 30, not 10.
Let's just take away from this example because it's confusing.
On the left side, you have 10, and the upper side, you have 30.
Let's use this example. I have a 10-foot mounting height. Cool? 10-foot mounting height. If I want to place this fixture to get a good rule of thumb distribution, I need to place them at, based on this ratio, the distance between a fixture divided by the mounting height is 2. Meaning, you're going to place them at 20 to center. Make sense? And then that will give you a good distribution rule of thumb. Again, I don't like to emphasize this one, guys, because we have a software, and we, based on the cutoff for 0.5, we were able to place them actually better, have a better judgment. That's if you don't have a software. That's a good rule of thumb to maintain a distance of 2 to 1 ratio between the height and the distance between fixtures. The height and distance between fixtures. Any question, guys, about this? The height and the distance between fixtures. And I can't emphasize that this area here, this is where the fixture are going to add each other. Every time they overlap, they're going to add each other's up. Every time they overlap, they're going to add each other's up. Any question, guys? Any question about calculating foot candle using a fixture outdoor? The only thing we did not take into consideration here, Ashley, we did not take into consideration the light reflected from the walls, the ceilings, or the floors, because there are no walls, ceilings. Oops, there is a ground, but we're neglecting. Thank you. We're neglecting the reflection from the ground. That's the only thing that's visual is doing indoor different than what we do outdoor. When we did the parking lot, visual have done exactly what we have done here, based on the IES file that we picked for that particular fixture. Any question? So that's basically what this calculation is doing. When we go to chapter 5, guys, which would be based on our calculation next week, we will do more calculation on this. We're going to take multiple points and add them up and find the average. And we're going to be using this formula for a while. So this is not your first introduction for this formula. Before I let you guys go, please go to page 47. Page 47 have a parking lot. And with the ISO foot candle curves for all the fixtures in the parking lot, exactly what you guys have done for our project. In page 47, you guys want 10 out of 10 in participation or no? Okay, page 47. Page 47, if you guys look at all these fixtures, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 fixtures. Can you guys see the 13 fixtures? Each one of them has an ISO foot candle curve. And I want you to, the only thing I want to highlight, see every time they overlap, that's what Andrew told you and I told you guys, when you put these curves, you overlap them. Because when you overlap them, you get the best distribution, slightly, not a whole lot. When you overlap them, I want you to see how the curve, each one of them is 0.12 foot candle. When they overlap, obviously, they add each other's up. Every time they overlap, they add each other up. So if you overlap a 0.12 with another 0.12, what's going to happen? You're going to get 0.24, right? Right at the intersection, So that's how your parking lot should look like, and I know you guys did that. I know that because we did it together. Your parking lot should look like that, overlapping. There's a couple of rule of thumbs, guys, you can read through right here at the bottom, how to place things, but we have the software, and it's really, the software give us much better than these rule of thumb. For example, they're giving you in an indoor, a room like this, if you have a 4-lamper, recessed, 4-foot fluorescent lamp, 75 square feet will provide a 75-foot candle. Take this. If you take that one right above your head, and 4 lamps, not 3 lamps, and and you have a 75 square foot area right in the middle of a 75 square foot area, it will give you at a height of 10, I assume the height is going to be typically 10, it will give you a 75 foot candle. So basically a foot candle for every square foot. But don't use these values because we already have a software where you can get a much more accurate values than this. Okay. Any question, guys? Anybody has any question about that? The only thing I would like to do, one little thing, and then I'll let you guys go. I want to take 1 point and do it together. I'm going to add one more point here on this calculation. I'm going to add 0.5, and I'm going to use an angle that we have and do the calculation for this 0.5. Let's use an angle that we have a value for it so we don't have to interpolate. I have 45 and I have 65. How about if I use 25? I'm going to use an angle 25. So I'm going to use, here we go. I'm going to use this angle right here at this point. I'm going to call this point point number 4. Point number 4. And at this point, the angle is 25. Okay? I'm going to go find the calculation at point 4. Let's do it together. I added 1 point at angle 25. At angle 25. And we'll just do the calculation for this point at angle 25. Because I had these done for you. Everybody got that one? The same fixture. I just want to find a 4th point at point 4. If you put the 4 here, by the way, if you put the 4 here at 25, would you get different numbers? Same number. No, there will be symmetrical between the two angles. So a 0.4 here and 0.4 here at the same angle will be the same. All right, so let's go to 25. 0.25. Everybody get that one? Let's go foot candle at 0.3, foot candle at 0.4. Okay, so let's go find it. Let's find foot candle at 0.4. At 0.4. Okay, the angle, Miss Q is 25 degree, right? And then we're going to go to the fig. So we know what the angle is. We're going to go to fig. So from here, we're going to go to fig 4.1 under page, I always like to write this one, otherwise you're lost. Page 40. And candela power, if you guys go there, you're going to find the candela power at this angle is 830. Thank you, Audible. 830. And what's the unit? Lumens, not dollars. 830. So now we're done. We have the candela power, we have the angle. Let's go straight forward and plug it into the formula. So foot candle equal candela power times cosine Q raised to the power 3 multiplied by maintenance factor divided by the height given to the power 2. Piece of cake. What's the candela power? 830 times, what's the cosine? 25 raised to the power 3 multiplied by, that was 0.9, right? 0.9 divided by the height is still continue to be 10 times 10. And what's the answer? I need 2 gentlemen or a gentleman and lady to come up with the answer.
5.6.
Wow. 5.56, 5.6. Would that hurt anybody's feeling? 5.6 foot candle. You have an Excel calculator that's doing it? Wow. Okay. Any question, guys? Straightforward. No gimmicks, nothing. Yeah. Any question? Any question, guys? So when we move next week to chapter 5, we're going to do more calculation of these at different points. I would like to thank you guys for listening to your friend Chad, and that's about it. Go eat. Please read these chapters, guys. They're really easy to read, very down to earth. If you're a designer, like my friend Nick, strongly encourage you guys, especially if you work for an engineering firm, to chase that licensure, certified lighting designer. This will give you introduction to the lighting science.